So in the question, we are given a matrix C, which is equivalent to a single transformation B followed by a single transformation A. So C is equal to AB. B is first, so it's on the right-hand side, and A is second, so it's on the left of B. Now, looking at the structure of C and the fact that it's got zeros in the top left-hand and top right-hand corners, and then numerical values that are non-zero in the other corners, this suggests to me that some sort of rotation matrix was involved. So if we remember, we've got a rotation about 0, 0 with an angle theta. The matrix for that is cos theta, sine theta, negative sine theta, and cos theta. And there are a number of different ways I can get that to become something. I'm going to choose the value that theta equals negative 90 degrees. And this will then give me a matrix which is 0 and 0 here, because cos of 90, cos of negative 90 are both 0. Now, sine of negative 90 in the bottom left-hand corner will give me negative 1, and then negative sine of 90 will give me a 1 here. Now, what does it mean if my angle theta is an angle of negative 90 degrees? Well, that means it's a clockwise rotation. A negative angle tells you you're going clockwise. A positive angle, by convention, is anti-clockwise. So this is 90 degrees clockwise. I could also have achieved the same result if I went with theta equals 270 degrees anti-clockwise, so positive 270, because that would give me sine theta equals negative 1 in the bottom left-hand corner and negative sine theta equals 1 in the top right-hand corner. But that's going to be equivalent to doing 90 degrees clockwise. So that's one possibility, which gets me to this stage over here, but that then doesn't give me the 3 I need in the top right-hand corner. Now that's looking like some sort of stretch in the y direction. So if we remember that we've got a stretch matrix parallel to the y-axis, and if we want a scale factor of 3, that would be a matrix that looks like this: 1, 0, 0, and 3. So now we need to get the correct order here. So I am going to say that matrix A is equal to 0, minus 1, 1, 0, and matrix B is equal to 1, 0, 0, 3. So the order in which we're doing the multiplication, if you remember, we said C was equal to AB. So let's write down the correct order. And let's do the matrix multiplication. So 0, 1 and 1, 0. Multiplying across there gives us 0 times 1 plus 1 times 0 gives us a 0, 0. And then if we go on to the next column, 0 times 0 plus 1 times 3 gives us a 3 in the top right. Then we go to here. Minus 1 times 1 plus 0 times 0 gives me a minus 1 in the bottom left-hand corner. And the bottom right-hand corner, to finish this off, negative 1 times 0 plus 0 times 3 gives me a 0. So that is equal to matrix C. So that is the correct order in which we do them. So my two transformations are, in order, B first, and B is a stretch parallel to the y-axis with a scale factor of 3, and the transformation A is second, and that is a rotation about 0, 0 with an angle 90 degrees clockwise. So, question 11. Let's take a look at part 1 here. So, the simultaneous equations can be written as V2 and I2 are equal to A, V1, I1. Now, go back to the simultaneous equations. V2 equals V1 minus I1 R1 and I2 equals I1. And we can start to think of this as a pair of matrix equations. So V2 I2 equals, and then in a matrix, V1 minus I1 R1 and I1. And then the right hand side has got to come about by doing some sort of matrix vector multiplication here with V1 I1, and then this matrix here is going to be matrix A. So we just have to get the coefficients right. So we know that this part of the matrix will multiply by V1 I1 and we'll end up with V1 minus I1 R1. So it should make sense that we have a 1 here, so we do 1 times V1, and then we have a minus R1 over here, so we do minus R1 times I1, and it gives us that result there. Now in the second part, we have only got an I1, so whatever goes here must multiply by this to leave us with just I1, which means we don't need a V1. And so that means we've got to have a 0 over here, so 0 times V1 is 0, and we just need a 1 over here. So our matrix A is equal to 1 minus R1 going horizontally, 0, 1. Now we can do the same for part 2. Writing down the matrix B for type B. So in B, you've got V2, I2, which equals some matrix, which remember is matrix B, multiplied by V1, I1. Now look at the simultaneous equations that we've got here. So we've got V2 equals V1 for the top. So that means we need a 1 here. So we do 1 times V1 and a 0 here, 0 times I1 for the top row. And then for the second part, we've got I2 equals I1 minus V1 over R2. So that means we need a minus 1 over R2, which will multiply by the V1 to give us this bit over here. And then we just need a 1 over here to give us the I1. And again, you can check this very easily by just performing the matrix multiplication and finding that you get to these simultaneous equations afterwards. Now, part 3, we want the matrix which represents the effect of type A followed by type B. That means the order is BA, with A going first, B going second. So that means we need to do a matrix multiplication of these two matrices. So let's do that very carefully. So 1, 0 and 1, 0 gives me a 1 in the top left-hand corner. 1, 0 and minus R1, 1 gives me a minus R1 in the top right-hand corner. And bottom left-hand corner, I'm going to get minus 1 over R squared, and then 1 times 0 is, of course, 0. And then to finish that off, I want to do the green one, and I'll highlight it again, this purple one over here. So that's going to give me a 1 take away, no, add, because it's a negative multiplied by negative, R1 over R2. So that's the matrix BA. Now part 4 says, is the effect of type B followed by type A the same as the effect of type A followed by type B? So this is type A followed by type B in part 3. So in part 4, what we can do is switch the order and have B followed by A. So we simply just write the matrices out in the other order. So matrix B is, of course, going to be applied first, effectively, and matrix A is going to be applied afterwards. So matrix A is 1, 0 minus R1, 1, and matrix B is 1, 0 minus 1 over R2, 1. And let's do our matrix multiplication. So we'll start here and here. So that's 1 times 1, which is 1, plus R1 over R2. So we can already see they're not going to be equivalent to each other pretty much straight away. We'll take the red horizontal and the blue vertical, 1 times 0, and then minus R1 times 1, so that's negative R1. And then we're going to do second row here, and then the red one up over here. 0 times 1, and then 1 times minus 1 over r squared, so minus 1 over r squared, and then finishing it off, green horizontal, blue vertical, 0 times 0, 1 times 1. So we actually end up with a matrix that looks very similar to BA, but they aren't the same, because you can see that on the leading diagonal the two elements have been switched, but on the other diagonal the blue and green elements are in fact the same. Right, so let's start off by working out the matrix D squared, because it's equal to B. So what is the matrix D squared? Well, D squared simply means we apply D and we apply D again. So that's AB minus BA, reading vertically down, AB minus BA again. And let's do our matrix multiplication. So we want this and this combination here. So that's A squared minus B squared. And then we want A minus B and minus BA. So A times minus B is minus AB, minus B times A minus AB again. So that gives me minus 2AB in the top right hand corner. Bottom left hand, bottom row here, BA, and first column here, B times A is AB, A times B is AB, so we get positive 2AB this time. And then lastly, we want this row and this column, so that's minus B squared plus A squared, so it's A squared minus B squared again. So that's vector matrix, D squared, and we know that's equal to B. So that then tells us that A squared minus B squared over 2AB minus 2AB, A squared minus B squared is equal to the matrix 1 over root 2, 1 over root 2, minus 1 over root 2, 1 over root 2. I'll just seal off that little bit of the question up there. Now this should make sense, and it is consistent, because you've got the same element here, A squared minus B squared, and that's in both cases equal to 1 over root 2. So A squared minus B squared equals 1 over root 2. And then if we look at this part over here, or this part over here, we can get our second result, which is that 2AB is equal to 1 over root 2. Now, I'm going to now rearrange this second equation. So it tells me that B is equal to 1 over 2 root 2a. Now I'm going to need b squared when I do some substitution in a minute. So b squared is equal to 1 over 8a squared. And then if I go back to my first equation over here, I've got a squared minus 1 over 8a squared equals 1 over root 2. But we could rewrite that as root 2 over 2 on the right hand side. Let's multiply through by 8a squared. So that gives me 8a to the power 4 minus 1 equals root 2 over 2 multiplied by 8a squared. So 8a to the power 4 minus 4 root 2a squared minus 1 equals 0. Now we can solve this by reducing it to a quadratic form. So I'm going to say that x is equal to a squared. And this then gives me 8x squared minus 4 root 2x minus 1 equals 0. And I'm going to simply apply the quadratic formula to solve this as simply as possible. So minus b plus or minus the square root of b squared, which is 32, minus 4 times 8 multiplied by negative 1, all over 2 eighths, which is 16. Now, we know that x has got to be greater than 0 because x is equal to a squared. So it's a square value, which means it's a squared value, which means it has to be positive or greater than or equal to 0. So that then means we can reject the subtraction element of the calculation, and x is equal to 4 root 2 plus the square root of 64 all over 16. So let's keep simplifying. X equals 4 root 2 plus 8 all over 16. And we can divide numerator and denominator by 4, giving us root 2 plus 2 over 4, and then remembering that x is equal to a squared, or a is equal to the positive root of x because the question tells us that a and b are positive values, a is equal to root 2 plus 2 all over 4. We could root the 4 if we wanted to, but it doesn't really make it hugely simpler. Now remember that b is equal to 1 over 2 root 2 multiplied by a. So that is 1 over 2 root 2 multiplied by the reciprocal of a. So that's 4 over root 2 plus 2. So we might want to simplify the 4 in this instance. So we've got 2 root 2 multiplied by 2 over the root of root 2 plus 2. And then this 2 and this 2 cancel. And we've got 1 over root 2 multiplied by 1 over the root of root 2 plus 2. And because there are two roots here, because this is a root and this overall is a root, we can combine them as one single product. So that's 1 over the root of root 2 plus 2. And that's our value of b. Now, the question tells us that b is equal to d squared, or d applied twice. Now, we know that b represents a rotation by 45 degrees anti-clockwise about 0, 0. So how do we achieve a rotation of 45 degrees composed as two separate but identical transformations? Well, that means you've got two steps in your rotation, which means d is a rotation by 22.5 degrees anti-clockwise about the origin 0, 0. Now, what do we know about a rotation matrix? We know a rotation matrix takes the format cos theta minus sine theta, cos theta. Now, if we want a rotation by 22.5 degrees anti-clockwise, then we would need to have 22.5 degrees as our value of theta. So cos 22.5 minus sine 22.5, sine 22.5, cos 22.5. Now, if you work out what cos 22.5 and sine 22.5 are equal to, then you will see that cos 22.5 is 0.92387 ... and sine 22.5 is equal to 0.38268 ... Now, remember that this matrix is D, but D was also written as A minus B, B, A, like so. And if you remember, A had that slightly complex looking value of the square root of root 2 plus 2 all over 4. Well, if you evaluate that, that's 0.92387 ... And if you evaluate the square root composition that we got for B, which was something like this, that works out to 0.38268. So what are the values of A and B actually equal to? Well, A is equal to cos 25.5, which is the angle of rotation, and B is equal to sine 22.5.